solids. Okay. This is a picture from Hurricane Katrina showing you the power of gases just in our atmosphere, right? So the hurricanes, storms, anything like that, that's a lot of power driven behind those molecules moving really fast and the power of the gases even in our atmosphere. Okay, we're going to probably get through all this today, so here's just a little summary. I'm not going to read through it. Okay, this was on your sheet. So like I said, most everything was on there. We talked about this. I think it was Nick or somebody back there mentioned that gases are much less dense. Okay, so if we look at comparing densities, so let's take water in all forms. It can exist as solid, gas, and liquid. Okay, when it's a solid, it's about 1, so 0.917 there. And then the density of it as a liquid, 0.998. So they're, pretty similar. Okay, but this does explain, why the solid, so ice, floats in liquid water, right? Because the ice is actually less dense than the liquid. But if you look at this, density of water vapor is much, much, much less than that of a liquid and a solid. And this is carbon tetrachloride, same idea. So the gas molecules are very far apart, therefore making the gas less dense. And this is just something you need to know. Your atmosphere is composed of 78% nitrogen. Okay, when I sometimes will ask this question to my students, what's our atmosphere made of, or the biggest component? Usually I get oxygen. Okay, yeah, it's in our atmosphere, and that's, pretty, I would think that that's a pretty good, guess, because we know we have to have oxygen to survive, right? Okay, but it's actually just about 20%, 21% of the atmosphere. So you can look through here, here's CO2. Okay, it's a very small percent. Okay, you might be surprised by that. Hydrogen, look, it's only 0.00005% of the atmosphere. This is on your sheet. We talked about this. They're here, but there's just some molecular theory, and kinetics just means the movement, okay, of gases. But basically, we've already covered this. So gases are in continuous random motion. Okay, they're moving pretty fast. If we heat them up, they move even faster. Okay, they exert a pressure. Okay, that's a big difference between our liquids and solids. Okay, so they exert pressure, and this is a variable that we have to look at when we are trying to do calculations. Okay, pressure is force per unit area. Once again, that's on your sheet there. Okay, and typically our units for pressure are millimeters mercury, torr, and ATM. Okay, and for different calculations, you have to use different units. Okay, so we're going to talk about that and differentiate between which ones to use. Okay, but the main thing is you've got to know this conversion. So just like on your conversion sheets where you've got 1 foot 12 inches or 1 inch is 2.54 centimeters or whatever it might be, 1 ATM is 760 millimeters mercury or torr. Okay, if you have 760 millimeters mercury, you have 760 torr. They have the same unit, so I don't really know why we have kind of have both of them. Torr is actually named after a person named Torr, so maybe they just wanted to recognize him. Okay, STP. So I got some questions about what that means. Okay, and we didn't talk about it long. We mentioned it quickly on Monday. Standard temperature and pressure. Okay, it's 273 Kelvin. Okay, and 1 ATM. Okay, so 1 ATM would also be 760 torr, right, or millimeters mercury. Okay. Okay, and this is a reference point for most all of our gas calculations that we're going to do. Okay, the 273 is the same as 0 degrees C. Okay, but what you're going to find in these calculations, we always use Kelvin anyways. Okay, so you really just kind of want to memorize the Kelvin part. So 273 or 273.15 and 1 ATM. You've got to know that, memorize it. When you see STP, that's what you want to think of. Okay, that's going to be plugged in to your calculation. Okay, and you did this in the lab. I think I remember Cassie asked what came up to ask about what was P2 or the T2, and then I showed her it was STP. Okay, and so that meant that you plugged in these. Okay, we watched a video on Boyle's Law, actually two. Okay, this was the one where you can go back as you're studying and watch those videos so that you can remember Boyle's Law. Oh, that was the video where the head went down below the sea level and it shrunk. Okay, so then you can rationalize, okay, what happened? And the pressure increased, therefore the volume of the head did what? Decreased, right. So there's an inverse relationship. So increased pressure, decrease volume. Okay, that's what Boyle's Law says. And mathematically, we would write it like this. Okay, P stands for pressure, V stands for volume. Okay, and you're going to see T here in a few minutes stands for temperature. Okay, these ones, if you want to write initial, that's fine. So P1 is your initial pressure. So what's your problem telling you is your initial pressure? What's your initial volume? Okay, and then P2 is your final pressure. I'm going to write this down. And V2 is final volume. Okay, so just like any other mathematical operation, we can, if we know 3 of those values, we can always solve for the other one, right? The one that's left. Okay, fortunately for you, I'm going to show you, so there's different calculations with every law or formulas. You really just need to know one. Okay, so I'm going to show you how you can know one, and then all in all, you really need to just know 2 for the test. So there's 2 to know, but we can combine all of these laws into one and just memorize one equation. So you really don't even have to memorize this one. We're going to put it all together here soon. Okay, does anybody remember Charles's Law? Or remember which video we watched on Charles's Law? Anybody? Okay. Yeah. So when it was kind of the old video, but I kind of like the guys. See, I wish they let us do that kind of stuff in class, but they don't. They won't let me bring chemicals down here. Very well sometimes, but liquid nitrogen's what he used, so we don't have any of that in our facility. And liquid nitrogen, has anybody ever seen liquid nitrogen before? Okay. So it's very cold. Okay, and so we took that. He blew up the glove. Actually, it was about 1 liter of just his atmosphere gas in there. Okay, and then he put it into the little flask there, and then added the nitrogen on top so it cooled. Okay, and so our relationship was a volume temperature relationship instead of pressure. Pressure is Boyle's Law. Okay, and whoops. Okay, this is a direct relationship. So if you increase the temperature, you increase the volume. So when he pulled it out and it started to warm up by just the room itself is warmer than, of course, the liquid nitrogen. Okay, and then it started to expand. Okay, so all of these laws are reversible. Okay, unless, of course, like you said, you busted your balloon or whatever it might be. Okay, and here I've said again, this is on your sheet, and then up here a couple times. Okay, whenever you're doing calculations with these laws, the temperature has to be in Kelvin. Okay, so if you're going to be given degree C most of the time because that's what we use in the lab, right? Our thermometer reads degree C. You have to convert that to Kelvin. And just add 273 basically. Okay, so this shows that direct relationship. So here's temperature. As you increase temperature in Kelvin, okay, you get this gradual increase in the volume. Okay, anything below this point, you're going to start liquefying your gas. So even in that video, I liked how he mentioned he held up where the fingers were. You probably couldn't have seen it, but it had actually liquefied. So if you cool a gas, especially if you compress it and cool it, okay, it's going to convert from gas to liquid. Okay, so if you start getting into real low temperatures, then you have to start. It's probably not going to be a gas anymore. It may liquefy. Okay, Gay-Lussac's law is also on your sheet. It kind of goes hand in hand with Charles, so that was kind of the egg in the bottle experiment. So you heated up the molecules in the flask. Okay, so as the temperature increased, the volume, so the volume of the gases increased. So it filled up that bottle. Okay, well then you put an egg on top, and you just dramatically change temperature because now you put out the flame. Okay, and so the air inside the flask is going to contract, right? And so that kind of pressure and that contraction allowed to suck the egg through because it's trying to contract back down. So that drastic change in temperature made the volume of the air in the flask contract in, therefore kind of sucking the, instead of air, there was an egg on top. And it's kind of flimsy, boiled egg, right? So it kind of can get sucked down in there. Okay, but Gay-Lussac's law, you've got that there. It just says that the pressure and the temperature have a direct relationship. Okay, and so you can combine. Here's Boyle's law. There's Charles's mathematical expression. Okay, but like I said, we really don't even have to memorize all this. Your book actually shows it this way, as the combined gas law. Okay, I don't really personally, just after, I used to show it this way because that's what the book had. But I've rearranged it to look this way for you to memorize. And it really, I have found that this just prevents mathematical error. Okay, so I would memorize this in this form. Okay, because it's linear, most students can rearrange and solve for the variable better than when it's not linear and they're confused of how to move it over and isolate the variable. It's not hard. It's just that it prevents error. So that's why I show it this way. So P1, V1, T2. I'll put it up here. Forgot markers again. Okay. You cannot forget, here in red, this is T2. So 2 means what? Temperature final. Exactly. Okay, and T1 is here. Okay, so it's common. This is not P1, V1, T1. This is P1, V1, T2. Okay, so don't plug in T1 there when you start these calculations. Okay, so what this is used for is when you have a gas at a certain pressure, volume, or temperature, and then you change it. Okay, and you want to find out, okay, if I change the pressure and the volume, what's my new temperature going to be? Okay, or there would be my new temperature. Okay, or if I change the pressure, so I had a certain pressure and then I change it, and I changed my temperature, what's the volume going to be? Okay, so you're going to be given, here you have 1, 2, 3, 4, 5, 6. You have 6 variables, right? You're going to have to be given 5 of those 6, and you just solve. So you just rearrange and solve for the one that you're looking for. Okay, for the combined gas law, so look at your sheet. This is very important. Okay, notice right here, it's in bold, combined gas law. As you go down, it tells you it's combined gas laws, blah, blah, blah. Temperature must be in what? Units? Kelvin. Okay, as for pressure and volume, it doesn't matter if you use milliliters or liters. Okay, you can also use, for pressure, you can use ATM or torr, okay, or millimeters mercury. Okay, doesn't matter. You just have to be consistent. Okay, you can't use for P1 ATM and then P2 use torr. Okay, that's going to throw your answer off. Okay, so let's look at this problem. We're going to walk through it. You have a sample of nitrogen gas that occupies 750 milliliters. Okay, so the first thing I do is I just start labeling things as P1, P2, V1, V2. Okay, so if that is what I have to start with, that volume has to be my V1, right? Okay, and I've got it written over here, so but I'm just walking you through it. Okay, and the temperature initially is 75 degrees C. Okay, first thing I've got to do is convert that degrees C to Kelvin, right? Okay, so I take plus 273 and I get 348. So that's going to be my T1. Okay, I've got all this listed, so Okay, and my pressure initially is 810 torr. So there's my P1. If you want to convert to ATM, then you can, that's fine, but you don't have to. It's probably simpler just to use what's given there. Okay, it's looking for volume. Okay, it says what volume? So that means I'm trying to find V2, right? Okay. Would it occupy at STP? So we're wanting to go from the conditions given to us first to what would the volume be if we change conditions to STP. Okay, you're going to be given ones like this, and it's going to require you to know what STP means, right? Okay, so STP means what? Temperature T2 is going to be 273, and P2 is going to be 760 torr. Okay, we're using torr because we have torr here, right? Okay, we could also use ATM if we wanted to. Okay. All right, so we're going to write out our combined gas law. P1 V1 T2 equals P2 V2 T1. So you got to know that. You got to memorize that. Okay, now it is a simple arrangement, a rearrangement. Okay, so just like hopefully all of you have done in algebra, if you want to look for V2, you leave it by itself on the side of the equal sign, and you move everything else over here. Okay, so if we want to look for V2, then we've got to divide by P2 and T1. So they cancel. And this is what we end up with right there. Okay, so what I have written over here is the same as here. Okay, all you do from there is plug in your values. Just be careful because T2 is up here. It's very common to accidentally swap these. Okay, so you take your P1, 810, your V1, 750, those are your initials. You take your T2, which was at STP, right? 273. Your P2 is 760, and then your T1 is your 348. Okay? Some people, personally, I just kind of go through what's given, and I just write out to the side what it is. Or you can list everything if you want to, like that, or, whatever you want to do. Okay, you multiply everything on the top, multiply everything on the bottom, divide this into that, and that's what you end up with. Okay? So the new volume, V2, is 627. See what you come up with for this. So you're going to use the combined gas law. So write out your combined gas law equation. Up here, go through, label everything. It's P1, V1, T1, T2. You're looking for T2. Notice you have ATM and torr. They've got to be consistent. Okay, I converted to torr, but you can convert to ATM. Bless you. B1 we can leave as milliliters. The 32 we have to add 273. Okay, so we get 305 for our T1. Okay, I converted to torr. You could do the opposite and you should still get the same answer. Okay, so if you wanted to convert from torr to ATM, okay, you would have gotten the same answer. Okay, to do that we just use a simple conversion. So there's 1 ATM for every 760 torr. So ATMs cancel. So if you're going from ATM to torr, you multiply times 760. Okay, if you're going from torr to ATM, you divide by 760. Okay, ATM is always going to be the smaller number. You're going to get a smaller number than you start with. So we get 380 for our P1. And then we want to know T2. So that's why I rearranged. Okay, and then 5 times 10 to the second is 500, so I just made that look a little different there. And then our pressure is 1200 torr, okay, at P2. Okay, so when I rearrange, I have to put P2 first, so 1200 times the 500, which is our V2. Our T1, okay, don't put T2 there, T1 is 305. And then our P1 is 380, and our V1 is 260. So you get 1852 K. Okay. You maybe asked for Celsius, so you have to always go to Kelvin first because that's what this is set up to be in. Okay, and then if I wanted to know Celsius, then I would just subtract 273, right? To give us, we wanted that. So if we took 273, this would be equal to 1580 degrees C. Okay, and there's that all written out, but we did it anyway. Okay, so I wanted to show you this one. It's really simple. It's just using Boyle's law. But I just want to show you how you can use the combined gas law. You don't have to memorize all the other ones. Okay, you can still use the combined gas law here, even when one of the variables is held constant. Okay, so if we have, let's write out first our combined gas law. So we've got P1, V1, T2 equals P2, V2, T1. Okay, if you read this, it says we have 12 liters at 1.2 atm pressure. What volume would it occupy at 2.4 atm? Okay, so basically you doubled the pressure, right? Okay, so what does Boyle's law say? If we double the pressure, what's going to happen to the volume? It's going to decrease, and it's in fact going to decrease by half. Okay, so I can already tell you the answer is going to be 6 because we have 12 liters. You double the pressure, you decrease the volume. Okay, but what I want to show you is how you don't have to know the Boyle's calculation or the Charles alone. You can still just use this. Okay, if it says that the temperature in moles, which we haven't really even brought in moles, but are held constant. Okay, all you would do is if you know they're held constant, you can either plug in the same number for T1 and T2, but essentially they're going to cancel each other, right? If they're constant, they have no part, they don't play a part in it. So what I do is I just cancel it, and there you go. You've got Boyle's law. You didn't have to memorize it separately. Okay, it just is built into the combined. Okay, if you would rather put a 1 and a 1 there, or it doesn't matter. You could use 1 million if you wanted to for the temperature and 1 million for T1. Okay, they're held constant. Okay, so all we have to do is, so essentially we're left with this. We're looking for V2, so we end up with this. Our pressure is 1.2, volume's 12, our P2 is 2.4, so you end up dividing, and so you end up with 6. Right? Does that make sense, everybody? You can still use the combined gas law, and if it says it's held constant, just mark it out or put 2 numbers in there that are the same. Okay? Why it will let me do it sometimes and not others. Okay. So here's a summary. Boyle's law says that volume and pressure at a constant temperature, and N is moles. That's what we're about to throw in. So N is moles. Okay, Charles' law, volume and temperature have a direct relationship, and then we're going to throw in a new law. And this is Avogadro's law. To me, it's kind of the simplest one because it makes kind of common sense once I explain it to you. But Avogadro, everybody remember Avogadro's number? Okay, same person, same guy. Okay, he came up with our number of 6.022 times 10 to the 23rd is equal to 1 mole, right? Okay, so when I think of Avogadro, I think of he's been a huge discoverer or background to moles, all right? So his law says that if you increase the volume, you increase the moles, which makes sense, right? Moles is a quantity, so if you have more moles, then you're going to have a bigger volume. Okay, just like if I have added more water to my drink here, I'm going to have more substance, right? I'm going to have more moles of water. Okay, so it's kind of common sense. Okay, but we can put Boyle's, Charles, Avogadro's law, okay, and we get what's called the ideal gas law. Okay, so this was the combined, I'm going to abbreviate, combined gas law, and this is the ideal gas law. Okay. This, probably more than anything, that even people that tell me, I took chemistry 20-something years ago, and I remember PV equals nRT. Like, it's just something that every chemist, if you've taken a class, you should have been exposed to this equation. Okay? And the difference between it, so if you're trying to do problems and decide, do I use combined or do I use ideal gas law? Okay, one hint here is that you have moles. You have some kind of, moles. You might be given grams, but we know we can always convert from grams to moles. Okay, here you're given a change of conditions, right? You're given initials and finals. Okay, that indicates to you that you need to use the combined. Okay, here we're not given, an initial and final. We're given a pressure, a volume, moles, R is a constant, we'll talk about that, and a temperature. Okay, but just like we did here, if we're missing one of these values, we can always solve for it, right? Okay, so we're going to do the same thing. Okay, R is the universal gas constant. Okay, so this was derived. We're not going to spend time talking about how it's derived because it would take us probably 4 days to do that. Okay, and so it is just a constant that you plug in just like you did in lab. And some of you had questions on it, which rightfully so. You hadn't been exposed to it. Okay, but it is 0.0821 liters ATM moles Kelvin. This is the unit of R. Okay, it doesn't mean you multiply anything else, or that's just the units. Okay, this number will be given to you on the exam. You don't have to memorize it. Okay, and I'll give you the units. Okay, if you plug in R, okay, just like we've been plugging in things all semester, okay, and you want your units to cancel each other. Okay, so for the ideal gas law, you have to use these units in the gas law. Okay, so if you forget, go back to where I've given you R, and you can tell what units you need. You need liters, ATM, moles, and Kelvin. You cannot use grams, you cannot use Celsius, you cannot use milliliters, and you cannot use torr. You have to use these units. Okay, we had in the combined gas law, we had a little leeway, right? We could use milliliters or liters. Okay, and that's stated to you in this packet, okay, in bold, right? For PV equals nRT, you don't have a choice. You have to convert if you need to. Okay, you're going to have to use this right here. Okay, no matter how much I stress it, some people will still not use these. Okay, grams and moles are not the same thing, right? Okay, so if you're given grams, you have to do what? Convert to moles by using the periodic table, right, and adding up the molar mass. Okay, so here's a good example here. It wants to know what volume would 50 grams of ethane gas occupy at 140 degrees C under a pressure of 18 torr. Okay, this is not really a hard one, but this is one where we have to convert everything we're given to us because it's not in the correct units. Okay, so I did this on purpose so you would see how you have to convert. Okay, so the first thing that's listed is our 50 grams. I can't find the pen. There we go. Okay, so we are going to have to convert that. So we're going to take 50 grams C2H6. What would that be? 12, 24, 5, 30 point, what did I call it over here? 30.08. So if we added up the molar mass, get 30.08 grams per 1 mole. And we end up with 1.66 moles. Or 1.67 is what I have there, so we'll make that 7. Should have just looked on the screen. Okay. Next, we have 140 degrees C. We cannot leave it as degrees C. We have to add 273, and that gives us 413 Kelvin. Okay. Then we have 1820 torr. ATM is always going to end up smaller, so if you don't put your conversion factor in right, you end up with a bigger number, you multiplied, and you should have divided. Okay, there's 760 torr in 1 ATM, and that gives us 2.39 So PV equals nRT. If we rearrange to solve for volume, that's what we get right there. Okay. Moles is 1.67. We found that. R is given to us. It's the universal gas constant. Here's the units. Okay. Our T is 413 Kelvin. Okay. And 2.39 ATM. Okay, so the reason your units have to be the same, so watch here. Moles, moles cancel. Kelvin, Kelvin cancel. ATM, ATM cancel. So what are you left with? Liters, which is what you're trying to find, right? Okay, so your answer is going to be in liters, not milliliters, correct? Because your units here are set up to give you liters. Okay? I'm not liking me today. Oops, there we go. Okay. This one we want to find moles. So if you're asked for moles, you automatically want to think of PV equals nRT, right? Because we don't have moles at all in the combined gas law. Okay. So if we take our PV equals nRT, it says we want to find moles. So if we rearrange, we just bring moles by itself. Okay, another one where we're told that the conditions are STP. So this kind of makes it easy for us, right? Because we know that STP is what? What's our kelvins? 273. So we already have our unit correct. Okay, and then what's our pressure? 1 what? ATM. Right, so you have an option. You're going to use ATM because we know we have to use ATM in this equation, in our ideal gas law. Okay, so pressure is 1. Okay, we're given liters, which is nice. Okay, if I was given milliliters, what would you have to do? Okay, so if I gave you 8,960 liters, then you would have to convert that, or excuse me, milliliters, you would have to convert that to liters, right? Okay, so be sure you can do that. Okay, so there's your volume. There's your R that's given, okay? And then your temperature is 273 because it says it's at STP. Okay, so we cancel ATM, ATM, liters, liters, Kelvin, Kelvin. We're left with moles, right? Okay. It also asks for mass. So we find moles, and then what do we do right here? What's this last step? Convert from moles to grams, right? And so you just multiply your moles times 16 because that is the molar mass of CH4, 12, and then 4 for the hydrogen. So you get 16. All right, go ahead and work this one. Okay, remember the 50 grams ethane, we just did that, and I think it came up, the moles was 1.67 or 1.66. You don't have to redo that. Okay, so you're given 50 grams again of ethane. So if you divide that by the 30.07 or 8 or whatever it was, you get 1.67. right, did everybody get 1.63? All right, anybody need me to go back through this? Anybody? I don't mind walking through it. Okay, so we're just solving for pressure. We end up with ATM, so I canceled the units. Okay, so everybody got 1.63. All right, perfect. Okay, two more main things to talk about today, and we'll have everything done and pretty much all the material for the semester done. So you should be excited. All right. Last two things. One is going to be Dalton's law, and you used it in the lab, so I'll kind of give you a reminder, kind of flashback to lab on Monday to help you. It's real easy. It's a subtraction. That's it. Okay. And what we're about to talk about now is standard molar volume. Okay, so this is something that you'll have to remember. Okay, there are 22.4 liters of any gas, okay, at STP, 273 or 1 ATM, okay, in 1 mole. Okay, this is pretty fascinating to me, probably not to you at this point, but for our solids and liquids, okay, we don't have a conversion like this. Okay, for your solids, if the mass is different, then they take up a different amount of space. So it's just like this doesn't take up as much space as that. Okay, for a liquid, same thing. Okay, if I have more water than somebody back here, you know, this is going to take up more space. Okay, for a gas, because they are so compressible and there's all these different variables to it. Okay, if you are at standard temperature and pressure, any gas, okay, people looking in here, okay, any gas is going to occupy 22.4 liters if you have 1 mole of it. Okay, so this is unique. So let me show you kind of a little picture to give you an idea. I can take 1 mole of oxygen, nitrogen, helium, hydrogen, argon, doesn't matter. Okay, if I'm at STP, they're all going to occupy the same volume. Okay, so here this balloon represents 22.4 liters. Okay, so we can't do this. We don't have a conversion for solids and liquids like this. Okay, we can take any gas and 1 mole of it, and it's going to occupy 22.4 liters. Okay, so that is a number that you want to remember, and it's called the standard molar volume. Okay, so it makes sense. Molar, moles, right? And then volume, liters. Okay, so we have units here of moles and liters, right? So that's like molarity in a way. Okay, so we're going to do some problems with this. And all you really have to remember, so most of it's just going to be repeat of grams to moles or moles to grams. Okay, but now we have this other conversion. Okay, so if you look up here, you may not even have to go through the whole plan, even though I'm going to show it. If you have 2.75 moles, okay, of any gas at STP, okay, then what's the volume going to be? Can anybody rationalize that in their head? What are you going to do? You have 2.75 moles. Okay. We said that if we have 1 mole, it occupies 22.4 liters. So if we have 2.75, don't you think we'll probably just multiply 2.75 times 22.4? Wouldn't that be what you'd rationalize in your head? That would be me. Okay, so let's show that. Our conversion factor is our liters and moles. Okay, you can look at it this way or flip it, right? Okay, so we take 2.75 moles, and in every mole of any gas, here it's nitrogen, it could be oxygen, it could be whatever gas we want to use, okay? The key here is it's at STP, so you have to pay attention to that. It has to say that in the problem, okay? So moles cancel. You're left with liters on top, right? And that's what you're trying to find. So you take 2.75 times 22.4. Okay, if we were given grams of the gas, what do you think we would do? what would be our plan to get to volume? Yeah, you would take grams, convert it to moles, and then multiply, right? Okay, so we're going to look at two more scenarios. All right, so we're going to try to find the answer to these. So here's two problems. We're going to actually, they're on the same slide, but we're going to work through the first one and then come back and work through the second one. Okay? So it says, what's the volume at STP of 4 grams of methane? Okay? So exactly what Abdullah just said. Okay, he already came up with his plan. He said, well, if I'm given grams, I know I can go to moles, right? And then I know I have a relationship between moles and liters. Okay? All right, so take just a couple minutes, and I want you to try to answer these without us even going over them. Okay? This one, you're given liters, so you're going to go backwards from the first one. You're going to go from liters to moles to grams. Okay? All right, so take a couple minutes and try to answer these. See if you get A, B, or C for these. So think about what conversions you'll have to use. If you have grams, you're going to have to add up the molar mass. So you're going to need grams per mole. And then you're obviously going to need your standard molar volume. All right, see if your plan is looking like this. Problem still up there at the top. Okay, the first thing we do is we always write out what we know, right? So the first one you're starting with mass, and the second one you're starting with the volume. Okay, so be thinking about these arrows like I always draw. What do you have to multiply or divide by? Okay, that's where your conversion factors come in. Okay, so number one, to get from grams to moles, what do we have to do? What are we going to have to? We're going to have to divide, right? We're going to have to divide by the mass of CH4, which we already earlier saw was 16, right? 16.0. Okay, and then to get from moles to volume, what's our new relationship between moles and volume? 22.4 liters per mole. Okay, that's what we're going to use there. Okay, here we're going from volume to moles. Once again, what's our relationship between volume and moles? Okay, 22.4. Okay, so we'll have to use that first here to get moles. And then to go to moles to grams, what do? We just simply multiply, right, by the molar mass. Okay, so if we think about what conversions we need, here they are. We need our standard molar volume. There's 22.4 liters in 1 mole. Okay, we need our molar mass, our grams and moles. Okay, we got to decide if they're going to plug in this way or this way. Okay, and we base that off canceling our units. Okay. Here we're going to need the same thing. We get 22.4 liters. And then here Now we're using helium. I think I thought we were using CH4 a second ago, but helium has a mass of 4. Okay, so that's its atomic weight on the periodic table. Okay, so we put these together, and this is what we should get. So we should get A and C if we look back at the problems there. We take our 4 grams, and we convert from grams to moles, dividing by the molar mass. And then to get to volume, we know that in 1 mole, there's 22.4 liters. So we should get 5.60 liters. Okay, and key here, we're at STP. Okay, the next is just in reverse, right? We start with liters and go to grams. Okay, so we have 8 liters. We know that there's 22.4 liters in 1 mole, and in 1 mole there are 4 grams from the periodic table. So we get 1.43 grams of helium. Okay, I think there's one more for practice. Okay, so if you understood those, we're going to check and make sure right here. Okay. So I want you to find the volume in liters of 64 grams of oxygen at STP. Okay. So just one more practice problem. Got an answer yet? 44.8. Anybody else get that? You got 44.8. What you got? Okay, what's our units? Liters. It's volume in liters, right? Okay. Y'all did that quick. Okay, so you take 64. Okay, O2 is 32 as its molar mass. And 1 mole, there's always 22.4 liters. Very good. All right, the last thing we're going to talk about is Dalton's law. And basically, it's pretty simple. It says that if you have a container, whatever that container may be, it could be the room, the building, whatever it is, okay, the total pressure, okay, in that container is equal to all the partial pressures or the pressures of all the gases that are in that container. Okay, so if you have hydrogen, oxygen, argon, or whatever is in the container, then the pressures of those gases all added up is the total pressure of that container. Okay, does anybody remember using P total in your calculations in lab on Monday? Okay, do you remember where you got that number from? From the board, from me, right? How did I get that number? Very good. Okay, I probably didn't see me, but I had to climb up high and look up there at our barometer that tells us the pressure of the lab. Okay, so whatever gases, hopefully it was just atmosphere gases in our lab and not anything else in there. Okay, but that tells me the pressure in the room. Okay, so that can you'll notice when it rains or different days, I can tell a pretty big difference in what the pressure of the lab is and the different temperatures and all that, which makes sense, right? Because gases can change based on that. Okay, so your P total was the pressure of the room that I read from a barometer. Okay, so it was the total pressure of any of the gases in that room all added together. Okay, so it doesn't matter. So you could be given. So I like to give something that's kind of wordy here, and it's actually just a very simple calculation. You just add, and the next one you're going to see we subtract. But you're at 25 degrees C, so we do want the temperature to be about the same. But most, in our lab, the temperature, well, lately the AC and the heater's been crazy, but normally the temperature in the room is not going to change dramatically. Okay, bless you. Okay, so all of this, it tells us that the pressure of hydrogen is 3 and the pressure of the oxygen is 2. So if that's all you have in the container, then you just add 3 plus 2 gives you 5. That's the pressure in that container. Okay, if you had another gas in there, then you would add the pressure of that to it. Okay, you use Dalton's law in a different way. Okay, so it's the same law, but I gave you P total. Okay, so you knew the pressure of the room. So you knew this. Okay, in one of your experiments, okay, you went to the computer, and what did you find over there? Do you remember? The pressure of what? The water. Okay? So you found the pressure of the water, and you knew the pressure of the total room. Okay? So you knew this is not water, but we'll pretend that that's water. Okay? So you knew this, and you knew this. Okay? So how could you find this? Subtract. So that's what you did. You took P total minus the pressure of the water. This is on the next slide. And then you found the pressure of hydrogen. Okay? So you did this by the volume displacement, right? So when you set it up and the water was displaced out of the flask, okay, by the hydrogen that was being evolved. Okay? So this is exactly almost identical to what you did. Okay? So we have a sample of hydrogen that was collected. So you all collected hydrogen by displacing the water, went out of the flask and went into the beaker, right? Okay. The total atmospheric pressure, that's your P total. That's what I gave you, was 748. Okay. The pressure of the water, so all you had to do was take the temperature of the water and then go to the graph and see what the pressure of it would be at that temperature. Okay. So you went to the computer or to a table and you found the pressure of the water. Okay? And then by subtracting, you found what's left over. If the total pressure in the room is 748 and the only other gases you have are the hydrogen and the water and pressures, then you would take 748 minus 24, and what's left over has to be the pressure of the hydrogen or the gas that you are looking for. Okay? Does that make sense? Okay. Good. There will be one like this on the exam. For some reason, it's often missed. Okay, I don't know why. It's just subtraction or addition based on what I ask you. Okay, so be sure that you do really get this. Okay, if you have any questions after the break, you can let me know. Okay, this is just a bonus. We're not going to go through that. We're not worried about that. All right. So for Monday, have your OWL done by class time. Do all your bonus work. Have it ready to turn in for bonus points. Okay, we will work problems and review the whole day when you get back. Okay, if you have any questions after class or whenever, please let me know. But otherwise, everyone have a wonderful Thanksgiving and have a safe Thanksgiving as well. And eat lots of turkey. I know I will. I'll be cooking a lot too. Yes?